all of you. I hope you can hear my voice because I have a low volume of voice. Good morning to all of you. I'm Vandi. I am a project manager of innovation for Focchi Group. Focchi is an Italian company who design, engineer, and manufacture bespoke curtain wall facade. And today I have the pleasure to present the Basajaun project, and where Focchi made and developed a bio-based curtain wall facade. So let's start with the overview of the presentation. The presentation is divided mainly in three different parts. The first one, I will give you a brief introduction regarding the Basajaun project, so objective, outcomes, and context. And then I will go through the methodology that we have developed and applied for the development of the facade system. And then some conclusion regarding the achievement and the results. Let's start with the Basajaun. So Basajaun is a European project, and it started in 2019 in October, and it is towards the end because it will finish next year in 2024 in March. It's a really big consortium because we are 29 partners, and we are spread all around Europe in 12 different countries. The coordinator is Tecnalia, and the person in charge is Javier Garcia. In this project, the role of Focchi is to develop a curtain wall facade system, including bio-based materials, because as you know, the standard for curtain wall facade is aluminum. In this project, we wanted to use an alternative material for this kind of system. What is the objective of Basajaun? Basajaun has a lot of outcomes, but the main objective is to boost the use of bio-based material in the construction sector. So today I will talk about especially regarding the facade system, but the goal of Basajaun is to face all the construction value chain. But in this presentation, I will talk about the innovation that we have developed, which is a facade bio-based facade, and how we will install in a real demo building. Okay, let's talk about the methodology. You can see here how we have divided the project. The first phase is the most, let's say, crucial one, because we identify all the facade specifications, so boundary condition, objective, requirement, and goal and target that we need to address. And then the core of the activity is the development of the facade system in itself. The third phase is the test and the result, because in order to validate the facade system, we had to conduct tests in order to validate and verify the feasibility of the facade. So we had conducted the performance mock-up, the acoustic, and the fire, but then I will go through all of that. Okay, just a context, because before starting with with the designing phase, we have analyzed the state of art and the needs. So we have been asked why we need to develop a bio-based component. So all of us knows that the construction sector is the sector which has a higher energy consumption percentage, and also 30% of the solid waste is due to construction. So what we wanted to try is to replace or also find an alternative to aluminum, because nowadays the traditional facade, curtain wall facade, are made by aluminum. I'm not saying that aluminum is not that sustainable, because in these days aluminum has increasing a lot of also its performances, because for just an example, but aluminum has a lot of a high percentage of recycled aluminum, so it's increasing a lot. But in this project, we wanted to try an alternative, to investigate an alternative for aluminum. So, what are the objectives and the role of the facade? The facade system, we can say that is one of the most important building components because it is responsible for the division between indoor and outdoor spaces. It provides safety to the people and also gives aesthetical appealing to the building. So three main objectives, and we could summarize in these three boxes. The most important one is to industrialize the process and the manufacturing process of the facade. So also in the designing phase, we needed to keep in consideration this requirement in order to make safe the transport, to make easier the transportation. So in terms of dimension, in terms of weight, in terms of workability. So easy to make easier the transportation and the installation activity. And then the second requirement is the customization, because we know that in construction, really important feature is to allow people and clients to have their own building with their own features and materials. So two main aspects for this. So we wanted to make interchangeable the cladding materials, and also to apply this solution in different kind of buildings, so residential building, office building, and so on. The third requirement was the one I mentioned before, is to introduce bio-based materials. The second phase for the analysis of the boundary conditions are the requirements that are compulsory to keep in consideration in order to address all the performances that all countries needed. So we made a really deep investigation all around Europe. In this table, there are listed just some requirements. We took in consideration Finland and France because they are the countries where the full demo cases will be installed. So we took this into consideration, while the third column is the summit of the previous one, and we took the requirement, the most restricted requirement, because what we wanted to achieve is to define a solution that could be used in different countries. So here I listed the more restricted. Okay, and let's start with the second phase of the methodology, the designing phase in itself. As you know, the curtain wall facade is a lightweight facade system without a load-bearing structure. So it has our own frame with perimeters, and it's literally hanged to the ceiling of the building. So let's say that one of the main important components of the curtain wall facade is the frame. In order to replace aluminium, we investigated different hypotheses and different scenarios. We started with wooden profile, or wooden profile with pultruded profile. So we try to combine different technology in order to select the most convenient one. So we did some thermal performances, and at the end, the conclusion is that the solution which has the lowest transmittance values is the one with wooden profile and pultruded profile. But we selected the pultruded profile. Why? Because the transmission values, the differences between the values were really low. So we decided in order to address the requirement of industrialization, we wanted to reduce as much as possible the number of components, because if we produce 1,000 square meters of facade, also having one single solution will increase a lot cost and time. So it is crucial to understand also how we need to address all this requirement. I want to spend some time regarding the bio-based component, because let's say is the most innovative part of the facade. On the right, you can see the section of the bio-based component, and it has been manufactured by a Hungarian company together with Amplas and Omicron. So they are two partners of the consortium. And after tried a lot of materials, this is the final composition. So this profile, which is really, the section is really similar to the aluminum one, there are some differences, of course, but we could use it as a profile for the Gutenberg facade. It's made by wooden fiber, basalt fiber for 60%, and these fibers are kept together with resin. We wanted to increase a lot the percentage of bioresin, but of course this is one of the feature that will be improved, because in this part the resin is not just bioresin. We needed to add also some plastic. Another difference is between aluminum, that the profile is not extruded, which is a really high energy consumer process, but it's protruded. It's a continuous process, and it started from bobbins of fibers. They are kept together, and they pass through a bath of resin, and then they pass through a matrix, and then they are cut. So it's a continuous process in order to make these bars. There are some barriers, like this process cannot have profile more than 4 meters long, but let's say for buildings, the standard height is 3 meters and up. So for us, it was perfect. Okay, and this is the concept, the axonometric view regarding the component, the facade components. And we have developed 2 different typologies, the opaque on the left and the vision on the right. The main concept is, as I said, a structural frame, and from the indoor to the outside we have a plywood which guarantee the fire performances, because we wanted to use just a membrane as a vapor barrier, but we needed to have this component in order to address all the fire regulation, because one of the main issues was also to comply all the fire requirements, because when we work with the bio-based materials, fire is something that we need to work a lot. So from the beginning, we have a plywood, which is a fire reaction, is in class B1, so is a good materials. And then instead to use a mineral wool, which is a standard material for Gutenberg facade, we use wooden fibers, which has a really close thermal characteristic. And then we use a membrane, the ventilated cavity, and then the cladding. So it's a series of layers in order to comply with all the requirements. And on the right, there is the same profile with a triple glaze panel of glass for the vision unit. Yeah, of course, this is the final solution, but in order to reach this solution, we made a lot of hypotheses, a lot of scenarios, a lot of consideration again, especially for plywood and also for thickness. Another thing that I didn't say in the previous slide is that we want to optimize as much as possible the number of components. So also the profile. We made one single matrix for both mullion and transom, because usually in Gutenberg facade, mullion and transom are different. But we wanted to reduce the number of matrices because they have a really high cost. So mullion and transom are the same profile. So in this slide you can see 3 different typologies. The opaque one, the vision, the window, and the window it takes the facade system of the opaque, and we integrated a wooden commercial window and the roller shutter. It will be used in the French demo, and a standard regulation, a national regulation in France is that we could not use some wooden blindings, so they required aluminum blindings. Otherwise, we wanted to use something bio-based. Okay, some pictures. In the lower part, there is the visual one, and the upper part, there is the opaque, right and left, and in the middle there is also the window unit. Particular importance was also to make interchangeable the cladding. So the opaque presented some wooden lamellas for the French demo, while on the right there is another kind of cladding, which is a wooden deck for the Finnish one. Yeah, this is the section of the value-based profile. As I said, this profile section was used to both Transom and Mayon, and we integrated a single profile matrix to be applied in that profile, and this is allowed the engagement of one facade above the other. Okay, and of course, some simulation, mechanical simulation in order to validate the system. ENAR, which is one of our partners, took the biggest and the heaviest facade module in order to verify all the mechanical behavior for all the components. And again, also some thermal validation. We took in the middle, but also all the nodes in order to understand the thermal behavior of the system. And here you can see the demo building developed by Studio, which is an architectural firm based in the Netherlands. They designed the Finnish demo as a cultural building, while the French demo is a residential building. We wanted to also demonstrate how this solution could be applied for different types of buildings. And this slide, I think, is really important to understand the industrialization concept, because we wanted to reduce as much as possible the number of different facade modules in order to make easier the manufacturing, the shop drawings, the procurement phase, because if we have 1 or 1,000 of the same modules, it's easier it's allowed to be easier the process. So we have the 2 different dimensions. The biggest one is 1 meter and 20, and the smallest one is 80 centimeters. And different typologies like opaque, opaque with door, opaque with window, and also opaque with door and window, and a different glaze cladding. So it's not that we wanted to reduce, still reducing, but let's say there's a compromise between architectural feeling and industrialization, because otherwise just a box. So we need to find a compromise. Okay, the third and the last phase is, of course, when we have designing the facade solution, we needed to validate and test it. So here there is the first prototyping phase. I just briefly, I won't go too much deep, but I'll just summarize some of the main steps. Here you can see the manufacturing of our opaque facade. So let's starting from the profile preparation, sealing, screw, connection, and then we glue the membrane on the profile. In this slide you can see the wooden fiber field in the facade module for thermal transmittance for sure, and then the cladding. So in the next slide there are the final configuration of both typologies, so the opaque and the vision one. The first test that we made is the performance test. Has been conducted in Istituto Giordano, which is an accredited entity based in Italy, really close to Focchi. And we designed the performance mock-up in order to test all different scenarios possible. So we wanted to understand the behavior of facade module in the junction between window and vision, opaque and window. So it's tested in order to comply with all the scenarios we could have in a building. Three vision in the lower and the opaque in the upper part. And these are the results. We comply with the norms, the standard norms, which is the 13813, which is a European standard for curtain wall facades. Since this system is considered a curtain wall facade, we needed to comply with the standard, European standard of curtain wall facade. So These are the result, and we pass all the results. What we have tested is the air permeability, the wind load, the water tightness, and also the impact. So it was really important also to guarantee the safety for people in order to avoid any falls or damages. Second test we made is the acoustic mock-up for both the vision and opaque. This test has been conducted was conducted in Tecnalia, and we made different tests. So one specific for opaque and one specific for vision, and this is the result. In France, we didn't have a really high requirement for acoustic because the demo mock-up is literally in a forest. But in this case, we comply with all the requirements, so we were really satisfied regarding it. The fire mock-up, so as I said, the fire was the most critical part. So we needed to conduct 3 different tests. So we tested the fire resistance, the fire reaction, and the spread test for the facade. And you can see some pictures, the result, and we have been conducted for both. But in this slide, you can see just the opaque one. This is the fire reaction. It is the SBI test. It is different from the other one because it's made in a particular furnaces, in a middle furnaces, and the fire goes in the external part of the facade, while the fire resistance is from the internal towards the external part. And here there is the spread test. So how the fire could propagate in a vertical way from the external part of the facade. So yeah, let's get to an end. We can say that all the results that we achieved are completely in line with the facade expectation. So we address the under-industrialization, also for the manufacturing line and for the installing part. This facade solution is customized because it could be changed the cladding. Could also the same solution could be applied for different facade typologies, and it is made by various components. So yeah, we can say that we are satisfied and we address the objective. Of course, in order to improve, we wanted also to look forward and see, okay, this is the facade solution, but what we can do next, what we can improve after all this process. So there are some features that we wanted to improve. For instance, reducing the cost, because if we wanted to make a solution and scale up the solution, the cost has to be reduced. And also the weight and the thickness, because the weight is really important also for manufacturing, because for instance, aluminium can hold and can move by 1 meters of aluminium, 4 meters long, can be moved by 1 person, while the bio-based component was heavier, so we need 2 persons to move. So these are all considerations that we need to keep in consideration for further development. And also, yes, as I said in the previous slide, we wanted to increase the number of bio-based material, because as you saw, there are, most of them are bio-based, but we can still improve. So yeah, thank you for your attention. And if you have any questions, thank you.
Thank you very much, Laura, for the nice presentation. Someone has a question, yes, please.
I have a small question. Why did you use a basalte fiber with the pipe?
Yeah, this is a good question. We tried different configuration with different composition. Also glass fiber, we tried together with the percentage. But at the end, in order to comply with mechanical resistance, it was a matter of mechanical. So they tried to introduce basalt, and they saw that it has a good behavior, so we kept going with basalt. But yeah, it was it's a mineral materials, and yeah, it's strange for a bio-based component, but it works. So we were willing to try and test the behavior, so we were satisfied about the result.
Thank you.
Any question? In fact, I have some questions regarding the wet resistance of the biogas component. Do you think that this could be also used for, I don't know, for rooftops or something like that?
No, unfortunately not yet, not with this composition, because it has some, in the composition, the producer had some fire retardancy component. It had also some water repellent, but it's not enough for now because it was not in the object of this profile. It was for an inner layer. So yes, it could be also for storage. We could storage like for maximum 2 or 3 weeks, but it's not. It does not have any waterproofing behavior.
Well, so thank you very much,
Thank
Laura.
you. Thank you.
One question, right? Okay.
Thank you.
The next speaker is Joana Araujo from CENTI, and she's going to talk about the development of numerical models for predicting thermal performance of materials with improved ecological footprint as alternatives to standard EPS. Joana?
It's in the other.
Yes, so it is wait more. Thank you.
Hello everybody, I'm Joana, I'm from CENTI, and I'm here today to present a work that we did on the project steps regarding the development of an American model for predicting thermal performance of materials with improved ecological footprint as alternatives to standard EPS. In terms of agenda, I'm going to start to talk a bit about CENTI and doing a small presentation about the research center that I come from. Then I'm going to do a quick presentation about the STEPS project as a whole and in detail the development of numerical model that we did within the project and finish with final remarks. About CENTI. So CENTI is a multi-sectorial research center from Portugal. In that picture you can see our campus. We are a center that aims to promote activities of research, technological development, innovation, and engineering on the sectors of smart and functional materials and systems, and work with projects both UN funded and national level, and direct contracted companies. We are funded by 3 other research centers, CETIC and CEA, all of them directed to specific sectors. CETEV is a textile, STIC is a leather research center, and CEA is a mobility research center, and 3 universities, University of Aveiro, Porto, and Minho. As I spoke a bit, we are aiming to promote activities of smart and functional materials and systems, and we work with multi-component fibers, smart materials and devices, multifunctional coatings, printed and organic electronics, and embedded smart systems. And we also have a lab from prototyping and doing the industrialization of our developments. As a multi-sectorial research center, we work with almost all substrates that we can imagine: paper, textile, wood, concrete, cork, polymers, ceramic, and all in between. Our focus is on materials for sustainable industry, microfabrication and printing intelligence, novel sustainable composites fabrication and our pilot lines that allow us to upscale our developments. Also nanostructured solutions, energy storage and microgeneration, and automation and software. I have here a small video about some of our technical capabilities. Here you can see our reactors for small-scale synthesis, our characterization equipment that allow us to do the validation of our results. This one is to see the results on the skin. Our pilot scale reactors, our spray coating line, some of the developments that we do, the plasma technology that allows to do pre-treatment of materials, our simulation laboratory that allows to do thermal studies on materials, simulating the human body inside the climatic chamber. We also work with functional fibers and are able to additive the polymers. Then we can then extrude or use to produce fiber. The fiber can be a three-component fiber and also can produce polymers for different kinds of extrusion. We also have the smart materials that allows to do some printed electronics and physical deposition of materials. Here we are seeing the preparation of flexible electronics, and we also have a line to allow us to upscale the developments. In terms of not flexible electronics, we also have the ability to do the hardware and software that accompanies some of our projects. Here we are producing the PCMs that are inside of the equipment. And I'm not so used to talk about this part. And our design and engineering lab that has the equipment needed to do the prototyping and the production of different demonstrations for our developments. I think I can move on. In terms of numbers, at the moment we are more than 150 collaborative researchers with more than 117 projects running. We have more than 250 active clients, 52 active patents, 20 joint ownership applications, and 5 CENTI ownership applications. A bit more about steps, that's what will bring us today. So the project steps aims to develop a new advanced building production system, a Lego-like construction system. Here we can see the block that we are aiming to produce. This will allow us to build the construction blocks outside of the place that we are doing the construction and then bring them there. In this way, we can use more robotic labor and are less dependent on the resources that are at place where we are doing the construction. This needs to be a very small, very lightweight solution that adds some influence on results. And then these blocks like that can be used to produce houses. So in the here we have a block. They are going to be placed one on top of the other. We have 2 facades of OBS or plywood. In the interior, we have an insulation. In this case, is an EPS with graphite, and 2 walls where we are going to pass through with wood beams that allow the stability of the structure. And you can see here in this design the wood beams and blocks passing through them and are used to construct the walls. With this project, we aim to overcome three fundamental challenges in the building production. As I said, the increase of productivity of the building production processes, so we can do the production outside the place where we are going to build, and bring all the materials and just set up like a modular construction. We can have a sustainable reduction of carbon footprint. We are trying to achieve this using more sustainable materials in the construction, and also democratization of the building production process, where we are going to create components library of BIM, and the user can build this house like we used to do as when we were children, that build houses with Legos. We can do something similar, and with that automatically generate order and associated costs, and then the house is shipped to us, and we just need to set it up. For the interior, inside the we had two OBS and the nucleus. We tested two different structures, a monomaterial structure and a laminated structure. We started to test the monomaterial and then tried to laminate it with different materials to try and increase the results. But the structure is, because of the need to mechanical stability, the laminated facades needs to be very small and doesn't produce the best results. We also test materials, different materials. The standard EPS that we are trying to replace, because it was the first material identified to do this block. So we studied recycled EPS that is done completely with the recycled traditional EPS, recycled PET, EPS neoplast, that is a recycled, it has components of recycled EPS and graphite. We also try cork, recycled cork, and hemp. So for see which of those materials and what of those structures would be better suitable for the building of the block, we developed a numerical model for predicting thermal performance. Using ANSYS, we developed three numerical models. We started with a 2D model, where you can see the block design that you use with the two facades of OBS, the thermal insulation, and wood beam. And we only did half of the block because it's a symmetrical block. In this simulation, we focus on the heat transfers as thermal conductivity and natural convection, and we are able to obtain results like this one, when we can see the temperature of the different components at the end of the stability. So we can see the outside that was at 40 degrees, a summer day, a very hot summer day. The block, where you can see in this green splash, and then the interior of the house. And we can see that between the exterior OBS and the interior OBS, we have a difference of 18 degrees. And this was tested, and this study was done for the different materials that we are studying. And besides that, we also did a 3D room, a 3D model of a room. For that, we use a room with the dimensions 4 by 4 meters with 3 meters high ceilings. And for this one, we use its transfer forms of radiation and natural convection, because from our experience are the most significant ones for this kind of model. In this 3D model, we did two variations: a room without refrigeration system and a room with refrigeration system. And I'm going to show the results that we are able to obtain with the room with refrigeration system that allow us to determine the power needed to maintain the room at a temperature of 22 degrees. Here we can see the monomaterial blocks and results of the power spent to maintain the temperature inside the room. And you can see that at the pink, green, and orange, we have the results of the different kind of EPS. So EPS, a traditional EPS is the green one, and then we have the recycled EPS. We can see that the recycled EPS has a slight decrease on the efficiency. And at orange, we have neoplast EPS because of the graphite components inside of EPS that allow us to have a smaller conductivity and then be a better insulation. And at yellow, we can see recycled PET that has an even lower power need, and we also see a deviation in time, and this result was due to the fact that recycled PET has a higher inertia than the other materials. But the higher inertia of the recycled PET comes at a cost because it's a very dense material and so very hard to use in this context where the weight of the whole structure is very important. In regards of more multi-material blocks, the laminated blocks with the EPS nucleus and different facades, we are able to see that they almost all of them have the same compartment, and so we believe that that is not a suitable solution, especially because we compromise the mechanical capabilities of the structure. Here we have a synthesis of our results in terms of energy assessment in comparison to traditional EPS. We see that both EPS neoplast and recycled PET have an energy assessment increase of 12% of best results. So we can see energy savings of 12% in the case of EPS neoplast and 11% in the case of PET, and all the other solutions work worse than the traditional PET. Some of them very close, but all of them worse. In terms of weight assessment, because as I said, it is very important for the company that this is a lightweight structure. So we can see that almost all of them have a decrease on weight. So almost all of them were heavier than the traditional EPS, besides the EPS neoplast. And at the end, that was as you can tell here, that is material that the company ended up using. We are almost at the end of the project. So these are the results that we are able to attain with this simulation. The results were also validated using a methodology that we developed at CENTI that allow us to, with our climatic chamber, that allow us to validate these results. And we were able to assess that this material was better than the traditional EPS alternative. This project, I forgot to mention, is a Portuguese consortium where the House Lab is the construction company that is developing the technology with the support of University of Engineering of Porto and CENTI. And that's it. I don't know if you have any questions.
I have questions. Did you do any comparison for price?
Oh, yes, we did. The neoplast is slightly pricier, but the company was okay with that. Recycled PET has an even higher price, even higher weight, so the company shut it down. But the difference is very slim.
So right now the material is being manufactured?
Yes, we are doing the demonstrator.
And do you still have any certification of the material, or this is ongoing?
The certification of the block as an whole is ongoing, but the material itself, the APS Neo Plus, as a fire class of A fire class, it's water resistant, does not biodegrade. That was also important in the house. And that the material itself is certified, and we also did our tests to do the mechanical characterization of it.
And I have another question. Do you think that if you change the size or the morphology of the module, you can expect better results? Have you made this kind of simulations?
Yeah, we did not have the flexibility to change the block itself, the structure of the block itself. For example, if we increase the width of the block, the results will be better, especially in the laminated, because we are very small laminated width. But the company was that would increase the difficulty of the construction and the transportation.
Thank you.
Yes.
And do you see any trouble between the connection between the blocks? Or how do you connect them together?
They are we use they are stacked one on top of the other with wood beams, so they do not shift side to side.
Yes.
And at the top we do it's placed like a block, so they don't go up and down or down.
There's pressure on it.
Yes.
But in the junction between different elements,
No, I believe it's just on the top.
You don't put anything on the pressure.
Sorry?
There's nothing to.
No, this can be set up and dismounted with no problem.
and water penetration, water tightness is guaranteed by so there are some steps, so they are connected together.
Sorry?
Can you go in the previous slide? Yes, so when we one above the other, there is some connection that.
Yes, they have an indentation that allows them to stack together like Legos. Literally like Legos block.
Well, thank you very much, Joana.
Thank you very much.
So the next speaker is Etienne Wurtz from CEA-INES, and he's going to talk about EASI ZERo Project, that is low impact and balanced material system for zero energy buildings and renovation.
Yeah.
I have my presentation.
No, we're not. This is this one. No?
Yes. Good morning, everybody. I come from CEA-INES in France, which is the National Institute of Solar Energy. We're working on solar, all what concerns solar, that means cells, modules, but also building and even neighborhood. I will present you a project which is at the beginning, called EASI ZERo. We try to put together a lot of different companies which was interested by zero carbon, zero energy, I don't know. And we are at the beginning of the project, so we have different materials, and I will present some of them. I didn't have enough place to bring all the materials, but I have some of them. The TRL is low, and so we have some materials, and we need to continue to work on the materials, but also we plan to have some proposal at the end of the project for zero carbon construction or zero or low carbon renovation. The project could aim construction or renovation, but we decided to focus on renovation. As you know, it's more interesting today. You have here all these teams, mostly from France, Spain, Norway, and Germany. And here you have the agenda. So the idea is, you know, we plan to contribute to the reduction of CO2 emission, and so we say at least 35 to 2030, but at the end we would like to have some zero carbon building in 2050. That means a lot of work and a lot of evolution. And because we are working also in solar lab, the idea will be to reduce consumption, but also to increase the renewable energy, solar, and we would like to have this kind of zero carbon building renovation. That means a lot of insulation, but also PV, and we choose second life PV, because if you want to have a very low carbon, you need second hand PV. Not you will use a lot of carbon also for the PV. So it's a huge goal, and for that, what we managed was we put together a lot of companies, and we will test the different products. We will see how we can renovate, have a wall component, and the issue is it possible to have a real component at the end of the project? That's what we will see during that presentation. So the different kinds of materials, some are well known like wood fiber, or what else? Even VOC paint is more and more known, and or insulated field accessories, some insulation in brick. But we have also some new materials like miscanthus. So miscanthus is a very strange material. You can smell it at the end, you will see. But we'll talk about later. It seems very interesting. Then I have some more wood fiber, and also you can see biopanels. Also about a little later. The idea is how can we have this low carbon material for the total envelope? That means we need all these materials. We will work on to test how we can have some component. Perhaps we will have different component at the end of the project. We will use different kind of materials. Some of materials help for the insulation, some other help for the health, and so the idea is what we plan is always something biosourced, because we answer to the call with that biosourced cycle, especially for the PV, and then some so integrated PV types, again, recycle if possible. Everything easy to apply, and always low carbon. So again, The idea is to have some package of insulating materials for innovation, and we will see, we plan to apply to a lot of different climates for. Here you have the different teams, and you can see that we have a lot of different teams from a lot of different countries, from university, research centers, some startups, some SMEs, and so the idea is it possible to propose something with so many different countries and so many different objectives with so many manufacturers, and you know that usually in open project it's difficult not to have a nice project, but at the end of a project to have something where different countries can work together. I don't have answer for the moment. So just to show you the different kind of material, so I told you about mycelium, so which something very new and I hope interesting. Wood fiber, you know, it's more known. Biopolymers, so even I have some new, I didn't know it before the project, but it seems very interesting for the windows, and so if I knew that, I would like to have it in my home. So water foam insulation is a kind of aerogel with close pores. Wood fiber, you know, it's more known. So phase change materials, something completely different, because it's not for the insulation, but for the inertia. Then painting, you see, that's for the health. And at the end, second life PV for energy production with very low carbon. Told you about some very strange material, which is a methylene-based product with very low CO2, and we can put it in wood fibers. Seems very interesting, and so the idea is you have some colonization, and you need a process with drying low temperature to stop this pollination of the mushroom insect. And Moklu is a small startup also who plan to develop this product, and again we will see what can happen. So how we manage the project? We have 3 scales. The first scale is to work at the lab scales, and with this kind of startup or research center, more focused on materials, because it's a project which mixed. So research center more focused on materials, other one more focused on building construction, and the idea is to have some something at this different scale from the material to the building. We will see different experimental testing at building scale, at wood scale, and we don't plan to have a demonstration at the end because the TRL of the project is low, but we will have different real use case, and when we get the first results at experimental scale, we can see by simulation where we can. Then the idea, another idea is at the end of the project to have some EASI ZERo community. EASI ZERo community with a lot of stakeholders. And that's a very interesting idea of the project. Means at the end of the project, we will not say, yes, we have a fantastic new material with, don't know, mushroom and biopolymers and something like this. But we have a community, and we plan to have a lot of different kind of people in this community outside of the project, and we have a lot of people interested already. And then we can discuss together and see if some of the material developed in the project are very interested. Some other one could be added in the community, and so the idea would be that the project continue after the end of the project with help of WDs or CDP, or we have different kinds of help that could be used to propose some network and then have a workshop to present what could be the future for the renovation. So then the different goals of the project, some very high objectives, that means less than 30% of CO2 emission with, for example, fiber or other things, 30% for the unboiled energy, so that means energy for the process. Then we test in depth, so with an experimental houses with two kinds of cells, and the idea is 20% of more thermal resistance and 30% less in the smoke stage. They are objectives, not we don't know what will happen at the end. And then the idea is to simulate different kinds of buildings. For the moment, we didn't completely finish to decide which kind of building we use, but we have 3 buildings which would be interesting. And so the objective is less than 50 kilowatt hour per square meter for the energy and 4 kilo CO2, which is kind of objective we can imagine with PV to go to zero energy and very low CO2. And to finish the team, so you have the different members of the team, and we are at the beginning. In the project between less than 1 hour, less than 1 year, and I hope we can show you very interesting results in 2 years.
Thank you very much.
Okay. Thank you for that.
Questions? Yes.
I have questions. What is the source of the second life items?
So we work with a startup, French startup from CEA. For the moment, we have a lot of panels from ENGIE, which come from plants, for very large plants, because if the industrial propose some economic models in 5 years, that means they propose new panels during 5 years for a large plant, and after 5 years they don't need them, and so you can have them for free. It costs more than as by panels in China, but they are zero carbon. It's not interesting for the price because you have to. This company, large company, don't want to continue with them because then they have the risk is to have different kind of problem, technical problem, and so they prefer to have new panels, and the technical model is done in 5 years. So it costs money, but it's and nobody know what to do with this kind of panel, and so then you have a lot of PV panels, and we need to build some commercial system which is what startup want to do. And the startup is involved in 3 or 4 projects that we have for the moment. And for the moment, it's only a startup, and we don't have a commercial system, but we hope to have.
Do you do repair or?
We test them. Yes, we can test, and so we don't repair. They are broken. We will do something else with them and try to get silicium or hope. But the idea is to keep the model which are not broken.
Well, I have one question. From the materials that you have shown us, which do you think that could have a good performance and be most useful from all the materials?
For which materials?
Yes.
I hope for all materials. No, some materials are very well known, like I can show you, but that's wood fiber. That's common, and we know the performance of wood fiber. The interest is it's zero carbon. These kinds of new materials. The question is not, I would not say about performance or the price. It's a possibility to have a lot of material. The startup told us always, yes, we have the possibility to have lots and lots, but for the moment there is no process, no industrial process. So it's easy to have it at a lab scale, but to have them at a very large, we don't know, but we need to help these kind of companies, and for sure in the future we'll have new materials, but at this moment we don't know which kind of material will appear in the future, and that's the real idea of the project.
If you look at the biopure window profile, there are transmittance of 0.8, more or less 30% less than the PVC or wood.
Yeah, it's fantastic to have this kind of. I think it's fantastic, but again, I don't know which will be the price, and same for you for the project. So at the end, if we have a good price and we're able to produce at a very large scale, so we'll win the market.
Okay. Thank you very much.
Okay.
That's any. So thank you very
Okay,
much,
thank you.
Etienne.
So I have some flyer if you're interested to find future new materials. You can have them.
Well, so now we have finished the first session. So see you at 11:30, I think, for the second part of the advanced materials paper session.
Good morning to everyone. Today I'm going to present mostly my work during a European project named INSPIRE, dealing with metamaterials, but on a different scope, on a different context, under the scope of a resilience analysis. So I will present briefly the definition and the design philosophy behind the metamaterials, and then I will try to integrate this material philosophy into a general concept of a resilience assessment framework. So, to begin quickly with the definition of a metamaterial. A metamaterial is any material engineered to have a property that is not found in naturally occurring materials. This how we translate this. Okay, obviously, almost every material that we use, or a big portion of materials that we are used, are not found in naturally occurring materials. But the special characteristic of metamaterials is the periodicity in their structure. So to give you a simple example, it's different if you put aside one layer of concrete and one layer of rubber instead of putting them continuously in 8 or 10 layers, concrete, rubber, etc. This can be translated into 1D periodic structure, working only on the one dimension, or also on 3D. On the 3D sphere, we can imagine that we may have a concrete beam, and inside the concrete beam to have some heavy inclusion, some spheres coated with different materials, also serving the periodicity law. So why do we need to do this? Because we have observed that this periodicity in the form can give us enhanced behavior and privileges on the dynamic field. Namely, the so-called band gaps are being created. Band gaps are considered to be attenuation zones for various waves transmitting through our medium. So, what we have to do, in simple words, is that we need firstly to calculate to define the frequency range of our waves and our hazard. That hazard may be a seismic one, a blast hazard, or any other dynamic nature hazard, and then to design our structure, our metamaterial, to block these frequencies. So here is a typical example of a band gap. We can see that this area is the first band gap, second band gap, third band gap. This is the area and the frequency range that the waves of these frequencies are being blocked or mitigated in a serious level, protecting this way our structure. With the red lines are defining the frequencies that are allowed to transmit without problem through our medium. So we need to focus when we design a metamaterial to have the desirable band gaps on the frequency ranges that are of our interest. Here is the periodic materials theory. This is the example of a 1D metamaterial. This could be any material AB. Also, it is not mandatory to have only 2 layers of different materials. You can have also 3 or 4 different materials. What we need is to have many layers, because we are trying to simulate the infinite structure into a finite number layer of structures, because of course we can't have infinite structure. Very quickly, this theory is exploiting the equation of motion for its layers, and we're using the boundary condition. The main, let's say, characteristic of this theory is that we're exploiting the Bloch-Floquet theorem. The Bloch-Floquet theorem is exactly a boundary condition that allows us to exploit the infinity of this structure. So with the Bloch-Floquet, we're considering that this unit cell, which is the 2 materials, are working. We're assuming infinite unit cells, so infinite layers of these materials. And what I want you to keep is this dispersion relationship. Based on this dispersion relationship, we are calculating the band gaps, having as unknown the K, the wave parameter, where we are scattering for various values of a K, and then we're taking the results for the real and the non-real values of omega, which is the angular frequency of waves. So, during my research within RINA and the National Technical University of Athens, we have dealt with the problem of the efficient blast protection of pipes towards blast loading. So what we proposed was to bond around the pipe this layout, which is of total thickness 40 centimeter, and we are placed in consequence layers of polyurethane foam and rubber. Here are the material properties. Again, as you can see, we didn't place 20 centimeter of polyurethane foam and 20 centimeter of rubber, but we prefer to place it with layers of 5 centimeter. Again, in order to have and simulate the infinite structure and to have the benefits that metamaterial concept can offer to us. So we studied two similar but not identical hazards. The first scenario was for band gaps for bent pipe towards surface explosion. The entry frequency range for explosion of this type was from 0 to 200 Hz. And this is because, as you can imagine, the soil is cutting, let's say, the higher frequencies of blast loading. So in the end, the final pressure loading of in our buried pipe is of this frequency range. In opposite, for the above ground pipes and free air explosion, the blast, the frequency range is varying from 10 to 50 kilohertz. Of course, after let's say 500 hertz, the quantity of energy transferred within these frequencies are not the destructive one for our pipe. These we can easily observe this if we can make a Fourier transformation and see how the energy, let's say the energy within which frequency ranges are has a bigger portion of them of the energy. So here we see the band gaps. The band gaps here are more, let's say, extended because also we are examining a huge range, a big range of frequencies. But here, just to give you an idea, after 200 hertz, the median value of real frequency range, of real frequency values, which means that these frequency values allow waves to transmit our medium, is for 3 hertz. So practically with this solution, after 200 or 300 hertz, we have secured our pipe towards these hazards. On the other hand, for the buried pipes towards surface explosion, we have, let's say, more. We have better performance in the end, better results, but our band gaps are not tackling exactly the total range of the free transmissive frequency values for the blast waves. So we have studied, we have made a numerical analysis in Abacus for various explosion scenarios, mostly of low to medium value of TNT quantity, because as you can imagine, for higher for explosions of a higher magnitude, like a bomb or an extreme terrorist accident or event, we can't offer with these feasible solutions effective protection. But for low to medium scenarios, maybe on for damages on urban level, where the bombing and the huge explosives are not the common let's say, solution from, is not the common dangers for energy infrastructures. We can see that we are varying from 50 kilogram of TNT until 400 kilogram of TNT, and for distances near and close to our pipe, because if we are simulating the explosion right in 0.5 meters above the pipe, then only from the destruction of the surrounding soils we will have tremendous displacements. So these are some results, both numerically and qualitatively, for the case of the buried pipes. With the constant line, we see the displacements without the beneficial presence of the metamaterial layout, and the dashed lines are for the cases with the presence of the layout. Of course, we can mention here that the buried pipes from the beginning are not having extremely big displacements. Let's say it's for the magnitude of 8 and 10 millimeters. But these are serious ones regarding the response of the pipe, because we must not forget that we're talking about pipes underground, buried, which are having also the loads from the soil. In this case, we can see that the danger, the hazard for our pipe is eliminated. Okay, we are having displacements under 0.1 millimeter. So we are practically isolating our pipe towards this blast hazard. Again, this is in a different reference point for our pipe. This is for the pipe spring line. Again, we have the same response in qualitative terms. Okay, so again, we are having almost zero displacements with the presence of the metamaterial layout. Here, the results are, let's say, are showing in the best manner, in a more obvious and realistic manner, the presence of the metamaterial. Because here we have an above ground pipe where we have serious displacements. We're having displacements of 30 and 40 centimeter without the presence of the layout, of course. And we can see that the presence of the layout is mitigating these values with a median value of reduction of 50%. So also this is more realistic because many buried pipelines are built usually outside of the urban context, or to say differently, in the plants which are located mainly in an urban context, the pipelines are above ground pipelines, and this is where the explosion incidents are taking more place. So here is a more, let's say, general overview of how the metamaterials are protecting above ground pipes towards explosions. With the blue line, we can see the maximum displacements appeared during this event, and with the orange line, we can observe how this is the performance of the metamaterial layout is. We can see easily that for test case scenarios for when the magnitude of the explosion is becoming higher, then also the reduction is more obvious, because we are talking here about a percentage of 53 percentage of reduction rate. Okay, so this is for the spring line and this is for the pipe crown. We are having a similar performance to these two reference points for our metamaterial layout. And here is where we will try to integrate these concepts and this philosophy into the general context. Try to be interdisciplinary, not offer only one solution out of a general context. Okay. Here is a resilience assessment method that we are using in RINA, and it's a 5-step methodology with system characterization, asset and event characterization, the impact analysis, and finally the resilient assessment. Just briefly, as a, let's say, is a classic type of resilience assessment method. Firstly, we need to collect various information about our system. Which type of system is this? Are we talking about energy infrastructures? Are we talking about transport? Are we talking about nuclear plants? All of these need consisting the first step of our method. Then we're delving into more technical details of our asset, like geometrical characterization or mechanical characterization. Of course, if we are talking about resilience on other systems, it's also organizational or economic characterization of the asset. And then we're proceeding to the event characterization. This is a very crucial step because based on this step, we will develop our risk scenarios, our risk assessment, our probabilities of the hazard. Of course, this step is not targeted only on one hazard, but we can offer. But this is also have the option of considering multi-hazards during the design of our resilience strategy and our strategy towards the enhancement of the resilience capacity of our asset or system. Okay, so mainly we have two types of hazard: the natural hazards, meaning earthquake, wind, floods, mostly related to climate change, and then we have also the man-made hazard, human error, terrorist attack, and more this year the cybersecurity events. So, as I said, the definition of the relevant hazard scenarios is really important for the accuracy of the resilience assessment method, and of course for this we need to have a reliable literature and data. These are the two final steps in which we will try also to integrate the metamaterials. Okay, there is vulnerability, consequences, and impact analysis. Starting from the previous step, where we have the data in order to develop our risk hazard probabilistic scenarios. We are processing and we are calculating via probabilistic modelings and risk assessment methodologies the exposure of our system towards a specific hazard or multiple hazards. In the end, we will have, let's say, an image of the vulnerability of our system towards various hazards, And then the final step, of course, is the resilience analysis. So in the resilience analysis, considering mainly also the cascading effects of a disruptive event, but also the interdependency of critical infrastructures and the connection with other types of systems for our system or asset. The analysis considers robustness, rapidity, resourcefulness, and redundancy. In the end, through a matrix, let's say, and indicators, we are having a final result. We know we can say to an operator or to governments that these systems is having problem there or there and there in a quantitative form, because this is let's say the difficult part in resilience analysis. Try to translate a resilience analysis into quantity values, and how we can improve these values by making certain attempts and certain reinforcement on our system or asset. One way to do this is, of course, the metamaterials, as we said before, because with the metamaterials we can offer protection toward dynamic nature hazards, which are hazards of high destruction capability for our structures. And they can offer in sometimes also not explicitly for one hazard, but towards multiple hazards, like for example, both for blast hazards and low vibration hazards coming from a nearby railway, for example. So what we can do, and what we are trying now to develop within RINA, is to try to implement metamaterial concepts towards our asset in a way to improve and enhance the resiliency capacity of our asset, and then through comparative studies with and without the presence of the metamaterial layout, like we did again previously in the pipe, to see how this is securing and covering the vulnerabilities of our asset and system. And then finally, of course, the resilience assessment, this will be translated also into better values in the final resilience assessment. Some potential meta concept of today and the future, because this is a design philosophy that for the engineering, regarding the engineering, the civil engineering practice has been developed mostly recently through the previous decade. So already we have, let's say, imagined some concepts, but we don't have succeeded to complete these studies. There is a huge interest worldwide, I believe, or I want to believe, for this design philosophy so far. So some extra concepts, metamaterial concepts, can tackle various hazards like surface and underground explosions, underwater explosions for offshore wind turbines, and the seismic protection of course, of city buildings. This is also a part, a field where we have much literature offered, but also for energy infrastructures like electricity and nuclear plants. For some of these concepts, of course, we have already literature, so if you want to delve more into this concept, feel free to contact me, because also from the rest of the consortium we have really interesting concepts on this. So, thank you very much for your attention, and I'm happy to answer to any answer you may have.
Thank you. Do you have any questions? Okay.
Scale of production.
What?
What's the reproduction of metamaterial?
Yes, we have in RINA, we are trying and we're working towards this, but we have already some concepts implemented, metamaterial concepts. Namely, we have a meta foundation which was for a fuel storage tank in Italy. And we have also experiments, namely on nuclear plants. We have experimental validation of these concepts, but until so far, I believe that a real scenario is the one I mentioned with the fuel storage tank.
Did you implement them in glass?
In glass?
Yes, for anti-seismic glazing.
If we have used glass in our metamaterial,
No, metamaterial in glass. Have you tried?
no, I don't think so. So,
Well, I have one question, but probably you have explained it before, but in my mind, when we talk about infinite material made on different layers, you are creating more and more interfaces between both materials, and this is something that is not so good when we come to ruptures or something like that. So can you explain me a little bit better which is the role of these different interfaces when it is exposed to hazard and how this hazard or these earths are dispersed in the material?
okay, yeah, I will, of course, I will go back here. Okay. It is not so matter of interfaces. We are trying to have as many layers as we have because we are considering that the medium is performing and the behavior is of a continuum medium. So we don't do anything special on the interfaces because we have also the boundary conditions are for interfaces working in accordance the one with the other. I mean that with many ways they are bonding together, so we're considered that they are working as one medium. The theory behind this is that we consider that we have an infinite layers because the theory of the periodic materials is working and is expressed for infinite layers. But in reality, we can't have infinite layers. So what is of our interest? If we are having at least 6 or 8 layers, we are considering that we are closer to this behavior of the infinite structure. And the thickness is not a matter. It's not that if we have 5 centimeter or 10 centimeter, it's better. We are care about the number of the layers. So theoretically, if we have 2 centimeter, 2 layers, 15, 16 layers of 2 centimeters, it would be better. But of course, in this case, the numerical calculations are a little bit more difficult. The feasibility of the solution also is not so enhanced. But this is what the Bloch-Floquet theorem is doing. Okay? The Bloch-Floquet theorem here is replacing the infinity of the structure in order to study only one unit cell, because the 2 different layers or the 3 different layers that are reproducing themselves, we are considering them as units.
Thank you.
Sorry, and one last. Also, this is the 1D. Okay, if it's more easy to imagine it, imagine, as I told, a beam with spheres inside, with coated materials.
That's good. Well, thank you. Oh, thank you very much. So So our next speaker is Kim Wang from KTH, and he's going to talk about the HYSTORE project.
Yes. So, thanks. I will start my presentation. And actually, the topic I'm going to present, it's not very much focusing on the material itself. So it might be a little bit outside the scope, but it's an application and a control aspect about the materials we have been involved in the projects. So the title is about a framework of hybrid control of thermal storage connected energy system. And the project we are involved just started 5 months ago, so it's not a lot of result yet. But we want to present this concept, and also we have some other projects we want to link with as our project. So first of all, I want to acknowledge both HYSTORE project, which is newly founded, and also our sister project, Hypergrid, that we have been very much based on the results from our sister project. And also, I would like to acknowledge European Commission for the funding and Swedish Energy Agency for the work, and all the authors who have been contributed for this concept. So, a little bit the motivation of the work, because thermal storage has becoming very important when it comes to demand flexibilities. So this is one of the topics we have been discussed a lot. And also one of the challenges how we can scale up the thermal storage, for example, using excess electricity instead of batteries, but using thermal storage. And also we want to reduce our footprint, and usually thermal storage solutions are much cheaper than batteries and other type of things. So we want to scale up this. And another motivation is that we want to integrate the thermal storage solutions in the energy network. This means, for example, low temperature district heating that we are converting into the new generation of energy networks. And another thing is that we are coming from energy control background, so we are very interested in what are the alternatives to control the integration of thermal storage into the overall energy network. So in this case, we propose some different concepts, how we can do the modeling, how we can control it, and what could be the co-simulation method we go forward to scale up the solutions. Yes, a little bit the concept of the HYSTORE project. In principle, we have engaged different thermal storage solutions on building site, and it could be on one building scale or multiple building scale as a multi-agent systems. And we are very much interested in the aggregator part, how the thermal storage itself can be integrated with different, say, building HVAC solutions or heat pumps, or the district heating as a big storage solution. And overall, the target is a grid. So how we can utilize these solutions to really shift the peak load for the grid and release capacity for the grid by using thermal storage. Yes, and the overall goal of this study is, as mentioned, we want to explore some new method to control the energy system that is within thermal storage. The first one is to use different machine learning models from both component level to system levels. And because so far a lot of machine learning method has been explored on the component level, low-level controllers, but now we want to scale it up to see if this different method can be used on the energy network as a whole not only HVAC or the component, but at a scale. And the second motivation here is really to generalize the machine learning model here, because so far most of the models we have been using is very designed to one solution or one component or one manifold for like floor heating. So we want to generalize the data and the data-driven models to see if we have a better framework that can work in principle with different components and different say requirements, just to have small adaptations. But the model framework is there that we can use code simulations for this. So here is a flowchart. We have been working with the concept. So basically, this is a control approach we have been thinking using, for example, limited inputs like weather data or temperature data, solar radiation as minimal inputs needed for the model. Then, for example, we take a PCM model with heat pump that combine this using optimization algorithm to see how this can be working using more data-driven approaches and see what the control actions would be in terms of, for example, both the thermal storage state of the charge, heat pump performance, and the potential to the grid contributions. So basically, basically the scope is to combine different components modeling and put it in a data-driven model and to see how the advanced control can be performed and how well it can be done in a real data set. So, as mentioned, that we are aware that there are many studies and projects have been working on this, particularly for load predictions, because in order to understand how the energy network works, we need to understand the load. That's the first step we need to know. But when it comes to electricity load, it has been a very advanced development and research, especially in academic environment. Many studies have been done for the load predictions, but of course, electricity load and thermal load are a little bit different. But the method also, we know that like AM model, CN model, and different model has been developed there. But what are the research gaps here? So what we want to explore from a research point of view is that can we really develop a prediction model that can generalize this? So not case specific or one topology specific, but rather general, in general, working with any energy network with different thermal storage solutions. This is very challenging, but we are trying. And the second research gap is, as we know that the electricity load is very fast, and we can predict this with different mathematical models. But the thermal load is rather slow. There's a delay of the demand and the supply. But also, we have found that the thermal load has rather linear patterns, especially if the building is a little bit bad and like with very little thermal storage itself, then it's somehow correlated clearly with a linear pattern with the outdoor temperature. So if it's higher, then you increase the load. And so, but the problem is that how we can combine these two different loads. Can we use data-driven model instead of getting all the good data, but we can generalize this, even working with low-quality data for both loads. So here are actually some challenges we want to explore. So I give you some examples of the load prediction model we have been developing. So in the core is a prediction model, and we have selected 2 days of time horizon and use time series data. This means that we pick some limited inputs for the prediction model, and we see that if the thermal demand match the model one match the real ones. And this is one result that we have found using our sister project, Hypergrid. This is real-time data in Italy. Now you could see that actually we reached some sort of good agreement with the true demand and the machine learning model here. It's quite challenging because what we want to do is that we don't care about what type of building it is. We don't care how people use it. To completely let the model learn itself and using 1 year's data that we don't know, and then use another year's of data, even the temperature outside are different, to see if this can be validated. So we reach some sort of mean square error of 4.01. This is quite good. So this step is quite essential for us to know because we need to size the thermal storage. So we need to know the load pattern behaviors better. And of course, this is based on an Italian case, and we want to further explore this in different climates. So if this can be even working in like Sweden or Germany with different temperatures to see if really the linear relationship impact how much the accuracies of the load. Yes, and another thing we have been facing the challenge is the co-simulation, because the research here has been done a lot, as we said, on the heat pump itself, on the thermal storage itself, on the building itself. But if you want to use any kind of data-driven method, you need to have a framework that all these components, you can let them talk to each other by a interpretable simulation environment. So this has been a challenging for us. So what we have found the solution is predict the temporal projections of a set of data independent variables. This means that you put different parameters from different components and try to set up a framework to let them run together in real time to see if this interaction can really meet the supply and demand. And the optimal, say, control framework will be sent to our algorithm or controllers to make sure this is the best decision. You can operate the overall network. And one thing is that in order to develop this co-simulation, the interoperabilities are very important because you may have different format of data, different time series, different interfaces. The heat pump manufacturers might be different. So we are still struggling with this, but we are coming to see the channel of the light of the channel. And here is an example we have been testing about the one thermal storage model that has been carried out by our partner CNR in Italy. And this is the testing rig we have. It's basically a simple storage tank with PCM in it. So the data has been done by experiment. So we have the real-time data. And instead of model this, we use a PIM model. This means a physics-informed machine learning in order to create a more generalized data, regardless of the dimension of the PCM storage, or trying to scale up to see if this PIM model can really work at a bigger level or smaller level. So basically, maybe you are familiar with this. So it's physics-based data-driven model. So you select limited parameters and to see how the AN training in different layers to meet the real data. So let the model learn itself. And we have also done some, say, previous studies to see if there are some good research evidence studies to show this will work with thermal storage networks. So we have, for example, concluded some advantages of using this approach or methodology is that instead of using pure machine learning, this required high computing power, and you need basically a supercomputer to perform the work. Instead, if you use PIM model, it's much easier for us. We can run it on your own PC because you have the mathematical framework to define the boundary conditions already. Then, so it's easier to consensus for the data. Then you can combine different physical parameters with the data you are processing. Yes, so basically from a computational perspective, it's easier for us for running with the modeling work. So also a little bit comparison we have done. For example, using our method with other method that is available, say in the research community. For example, comparing this with FEM, so finite element modeling, and this can be also similar to CFD modeling. So you need to compute all the parameters, define the boundary conditions, or actually run the experiment in order to get the data. But we have found some good motivations for us to continue with this research work because promising us a little bit more alternative how you can really predict the thermal performance instead of the conventional way, experiments, numerical solutions, or combination. But this is a little bit alternative in many ways, easier for the researchers. So that's my presentation, and it's a bit short, but
Thank you, Chen.
if you have questions, welcome.
Do you have any questions? I have one question.
Yeah.
It is related to your last slide about computational time. How much time do you need to run this simulation or this machine learning models?
Yes. So we did a comparison on using this model and the CFD model. So
Yes.
yeah, CFD model, we use the same data set we got from our Italian colleagues from the experiments. Then we put it as a validation data. Then the first is on CFD, it takes around 2 days. And for this, it's something like half an hour.
That's very nice.
Yeah.
Because there is also an important trend in the European Commission about the sustainability of the artificial intelligence.
Yeah.
And it is also part of a source of CO2 emissions to run this kind of solution.
Yes.
So that really nice.
And this approach is rather new with quite low TRL because it's not purely AI or machine learning. It's a combination of physics and machine learning, which means that because for any machine learning model, the convergence is a big problem. So in buildings like HVAC, I'm from HVAC control background, we use a lot of MPC, for example. And when you run MPC, for example, you need a lot of detailed plant data in order to create a reliable MPC model. But this can be done by machine learning. You just use the data to train and you validate, but it doesn't convergence. So one approach is you combine them both. So this is a little bit similar concept. You hybrid these two approaches to let the physics set the boundaries and let the data tell itself.
And I have another question because I didn't understand good when you told us that you can have discrepancies of the model if you test it or simulate it in other countries with different weathers. And why?
This is an interesting question because when it comes to thermal storage, we have say different solutions on the market. You have rather conventional thermal storage like a water tank that's sensible storage, and also you have other types are not really new but established like PCM, latent storage. So these ones are very much relying on the thermal load. Yeah, but also you have other type of thermal storage like TCM. You need to charge it by electricity. So this means that if you really want to generalize the thermal storage model, you need to understand loads not just from the thermal side but also the electricity side. So for the electricity, it's much related with electricity demand, but the thermal load is very much dependent on the temperature. Yes. So then you have this deviations that some buildings, like in Sweden, in Scandinavia, they are very heavy, and you can have the thermal inertia from 7 hours to 2 days. But some cases we studied in the northern part of Italy, it's thinner, so the thermal storage is rather small. Then the dependence of the temperature is different. So then the machine learning model really need to understand, can we have a general model regardless how heavy your building is, it can still predict accurately.
Well, my last question is, I have forget it again. What's important on the reader? I will talk to you later.
Okay.
Sorry for that. Comes later. Well, anyone has any question online? No. No. Also, thank you very much.
Thank you very much.
you probably know, in this session we have one speaker less, so we have finished. So if you would like to take some coffee, there is something outside, so that's good. And if you would like to stay here working, so well, thank you very much for the presentation. It has been a really nice session, and I like it very much. And it's very interesting. Thank you.